Folks, picking up right here with this chapter 8 on tunneling. So I may have to turn this into 2 lectures. I suspect this will be pretty heavy. So if I have to turn this into, part A and part B, don't be surprised. So let's get right into it. Okay. So by definition, tunneling is energy leakage by penetration through a classically forbidden region. Okay, so what does that mean? Well, if we kind of think about the particle in the box problem that we were just working on, we put a particle in this box, okay, and we said there's infinite potential energy requirement to get out of the box. So the particle is stuck in there and it ain't going anywhere, okay? So that would be an idea of something being, classically forbidden. Much like if I imagine a closed container with a marble inside of it, right? And I can shake that container around, and the marble can't get out. Okay, it can't escape. Well, tunneling is this phenomenon where I have a particle and I've placed it, into a box, right? Like we've done before. But now there is not infinite potential energy to get out of the box. There's some amount, some finite amount of potential. And tunneling can be observed over certain distances and certain energies. And what that shows is the particle can actually transmit through this barrier and end up on the other side. So similar to this example I just described to you of having, let's say, a closed box and a marble inside, if I was shaking it out, if all of a sudden that marble just penetrated right through the container, right, and without damaging it, I'm not talking about like firing a bullet through a piece of paper or whatever. If it just appeared on the other side, it will have tunneled, okay? So that's what we mean by energy leakage by penetration through a classically forbidden region, okay? So here you can see this wave function is showing us, typical wave function, oscillating sine or cosine function. There is an exponential decay through the barrier, all right? So it is, dampened. And then as it comes out the other side, it returns back to its oscillatory pattern with less kinetic energy than it had before, okay? So this picture isn't quite showing you everything that's going on. In actuality, we would have an incident wave as well as a reflected wave. So we could think of that in the wave-particle duality. If my particle, hit the barrier and then bounced back, okay, so we would expect to see a reflected wave. But also, the particle is able to transmit right through the barrier and then break on through eventually to the other side, okay? So it's a lot more complicated than just this simple picture. But all the same, using this one-dimensional concept and kind of borrowing some ideas from the particle in the box model, we can solve this problem. And that's what we're going to do next, okay? And so this has been broken up into 3 regions, region 1, 2, and 3. And we're going to solve the Schrodinger equation in each one of these regions. And I'm going to give you a little Easter egg here for your exam. I'm going to go through the ansatz method and show how we solve this problem. Okay, so what we know in region 1, we always know the Schrodinger equation. H psi equals E psi. We've also established that in region 1 and 3, the potential energy is 0. So region 1 and 3. And in region 2, the potential energy, has some constant value. Okay, but is not infinitely large. So now we can say then my Schrodinger equation in region 1 is only due to kinetic energy, right? So we've dropped the potential energy operator, okay? And so now when I go to solve this, I want to set this up in the reduced form. So let's do that. So the way I can set this up in the reduced form is by eliminating the constants in front of the second derivative and then rearranging the whole equation to be equal to 0. So doing that, I'm just going to write psi sub x right there to make my life a little bit easier. Okay. So, and then what I want to do here is multiply through by 2m over negative h bar squared through both sides. All right. And so now that's going to be negative 2me over h bar squared times psi x. And then now I want to rearrange this so it's all equal to 0. So now I've got my second derivative in psi. I'm going to add that over to the other side, plus 2me divided by h bar squared over psi x equals 0. So now there's my standard reduced form so that I can solve this thing. And remember, in the ansatz method, right, we cry, pray, guess, solve. So hopefully you've done the crying and the praying already. Now it's time to guess. And for all these functions, we're going to guess a solution to be, sorry, I'm going to write this over here to make some more room. Our trial solution, or our guess solution rather, is going to be e to the ax, which cannot equal 0, where a is a real number. Okay. So now I got to take the first derivative of that function, and that's ax, and we know that can't equal 0, and that's part of our guess. And then the second derivative will be a squared ax. Okay. Now I can just substitute these things into my reduced form here. We know d dx squared of psi of x, so travel along over here with me. So that's a squared e to the ax. Now plus 2me over h bar squared, so I keep all of those constants. And now I know here psi of x is e to the ax, and all of this equals 0, right, from my equation there. So I can eliminate the eax, okay, because it appears in both terms. So now simplifying that, that's going to, eliminate the eax. Okay, and now what I'm left with is a squared plus 2me divided by h bar squared equals 0. And now I simply just want to solve for a using algebra. So I can see here that a is going to be negative 2me all over h bar squared, and the square root of that. Okay, and so now this means we have an imaginary root situation. And I'm going to write the solution of this as I times k, where we recognize we're going to call the collection of all of these constants k, as we know, is the wave number solution to me over h bar squared. Okay. So now, because we know that psi of x equals eax, and we're saying a is I k, technically that's, because it was squared, we can make that plus or minus, okay? So what that means now is we can say that psi of x is going to equal, we need some normalization constant, a, e, I, k, x, plus some other normalization constant, b, e, negative I, k, x. And so this is our classic general solution for region 1, where we know this is this e, I, k, x and b, e, negative I, k, x. Those describe a wave function that is, a combination of sines and cosines. So it's a wave. It describes an oscillatory pattern. Okay. So I'll also write that we could write that in terms of sines and cosines, and we know either of these solutions are acceptable for the region 1. All right. So what about region 2? Okay, so here is what we know. All right. So now we know that in this region 2, my potential energy is constant. So we just have a constant potential energy there, okay? And we're going to consider cases in which V is greater than E, which that's depicted on this graph right here. So we're seeing that the potential energy is greater than the kinetic energy that the particle possesses, okay? And of course, in region 1, that kinetic energy is the total energy because that's all the energy that it has is kinetic, okay? So we're saying the potential energy is greater than the particle's kinetic energy. And so now setting up this equation, we know this is how we would set up the Schrodinger equation. And now I just want to do the same thing. I want to try to get to that reduced form, okay? So I can do that by writing second derivative of psi of x, okay? And then now what I'm going to do here is a couple steps at once here. I'm going to subtract the v psi over, okay? And collecting like terms, that's going to give me e minus v times psi of x, right? I subtract v psi over and then collect terms. And then also remember I have those constants that I want to push over to the other side. So that's going to be negative 2m over h bar squared, okay? And now what I can do is add that back over to the other side to get this into the reduced form. And so, you know, there's a couple different ways you could have done that algebraically. So pick your favorite, okay? So now that's going to be plus 2m e minus v all over h bar squared times psi of x, and that all equals 0, okay? Beautiful. So then now, if we continue along here, we're going to do the same method we did with the ansatz. Cry, pray, guess, solve. We've cried, we've prayed. Now it's time to guess. Okay, so we're going to guess the same guess solution, e to the ax. Okay, and so again, right away, we know that the first derivative of that guess solution is ax, and then we know the second derivative is the a squared ax, okay? So now I can plug these into my function right here, and let's do that. So second derivative of psi of x is a squared ax, okay? Plus, and then now we have all those constants again, 2m e minus v all over h bar squared. And we know psi of x is just eax, and that all equals 0, all right? Now we're going to do the same thing. We can eliminate the eax and the eax, and we get a squared plus 2m e minus v all over h bar squared equals 0. And now let's just keep this going, right? So now I'm going to say that a equals negative, so I'm going to leave this as a squared for the time being. So a squared equals negative 2m e minus v all over h bar squared. And now you might be looking at this and saying, well, this is going to be another situation involving imaginary numbers. That's what at least it looks like for the time being. However, okay, e minus v, we know because v is greater than e, right? Let's write this up here. We know that e minus v is actually a quantity that's less than 0. So we know that that term is already going to be negative, okay? So what I can do, I can factor out a negative and rearrange that so that it's written as negative v minus e, right? So we know that v minus e is actually a positive, okay? But if I make that quantity negative, right? If I say negative v minus e, then we know it'll have the same value as e minus v, right? And so now I'm going to rewrite my a squared as positive 2m times v minus e over h bar squared, Okay, and so now we recognize, so I can take the square root of both sides of that thing, right? And that's going to give me a real number, a real solution. Okay, so we'll say here now, I'm going to use a slightly different letter. I'm going to say now my solution for A equals kappa, so it's just a change of letter here, okay? So where, in other words, kappa, and so, technically this is, because it can be squared, right? It's plus minus kappa, right? Okay, where kappa is this square root of 2mv minus e over h bar squared, all right? And so what that means, my wave function psi of x is going to equal the following. So I'm going to just pick a new set of letters for my normalization. I'm going to say C, E, and now, so remember, A is really just plus or minus kappa. So I'm going to say kappa x plus dE to the negative kappa x. And this becomes my general solution, my unnormalized solution. And again here, I used a kappa instead of a k because we note here that the k that I came up with right here is the root 2me over h bar squared, all right? I'm going to use this letter kappa to be 2mv minus e over h bar squared, okay? And we can also see this is an equation of either, describing exponential growth in the case of e to the positive kx, and then exponential decay to the e to the negative kx. And we can see that, right? This is an equation describing exponential decay, which is pretty cool. Now, what about the exponential growth part? Well, as it turns out, if we were to look at psi squared, which is what this kind of picture is showing you right here, right? We can see, right, this region that's showing what looks like exponential decay, and this other region here that looks like exponential growth. All the same, what both of those functions are showing is this dampening of the wave, okay? So it's this exponential solution that's in here that shows a exponentially decreasing amplitude of that transmitted wave. So that's what both of those terms are showing you. And what you also might guess from the region 1 solution, where we got, e to the ikx and e to the negative ikx, right? The e to the ikx, we know, describes a particle moving to the right, so showing the wave front moving this direction. But the e to the negative ikx is really corresponding to a particle moving the other way. So that term we can relate to the reflected wave. Okay, so we can actually ascribe these solutions to their particle counterparts. Okay, and then finally, what we know about the region 3 solution, well, it's very similar to the region 1 solution. Okay, because potential energy is equal to 0, we have the same situation of kinetic energy, right? So basically, I'm just going to write directly, follow this region 1 solution. It's going to work out identically, okay? And we're going to stick with the e's, the e to the negative ikx portions here. So I wrote the c sine x, d cosine x. We're going to stick with the e's, okay? So then I'll just write directly the region 3 solution we know is going to be, I'll write it as a prime e to the ikx plus b prime e to the negative ikx, okay? Which again is, describing a particle moving this direction and a particle moving in that direction, okay? Which we could note, would describe our particle moving this way, but then eventually, right, if there was another barrier there, could describe a particle then reflecting back off of that barrier, all right? So let's summarize what we know, all right? And I copied these right out of the book because I didn't want to LaTeX it all, but right, this K, it's, region 1, A, E, IKX plus B, E, negative IKX. Here, they're saying K, H bar is the root 2 M, E, K. right where the EK, that's the kinetic energy, the initial kinetic energy this particle has. Right, I can write that also as 2 MEK over h bar squared, all square root. Right, so that's the same form that we came up with. Okay. Similarly, right here we use the letter kappa for region 2, and that's, I could write that as 2m v minus e over h bar squared, all square root. And then we recognize this k right here is 2me over h bar squared square root, where now this e will be different than this ek. Okay? So what do we need to do now? Well, we need to normalize all three of these solutions simultaneously to solve these boundary conditions. And it's a mess. It's a total mess. And I'm not going to require you to go through and do it all. I am going to set it up. And what I will say on this Mathematica 4 assignment that I've got here in front of me, there will be a bonus opportunity at the end of this for you to be able to create this plot that I've created right here. And we can only create this plot right here by being able to normalize all of these simultaneously. Okay, so let's just set it up. All right, so one thing we need to recognize is we need to normalize all three of these functions together such that their values are single valued, right? So in other words, if you look at this wave function in region 1, it's just got to smoothly transmit right through region 2, and then similarly, the region 2 solution has to smoothly transmit through region 3. So that's just one of the requirements of wave functions, right? That they have to be single valued. Another requirement is that it has to be continuous. So you can see here, this is showing you the slope, this blue line that I'll dot right there. That's showing you that the first derivatives across those solutions have to be continuous, okay? So if we look now, summarizing these three regions, what do I have right here? Okay, great. So let's build up these solutions. So the first thing we note is the values of psi have to be all equal to each other, okay? And so I'm going to define this in my picture here. I'm going to call this border the first place of the barrier, x equals 0, and I'm going to call this boundary x equals L, okay? And so what this means now, let's see. So in my region 1 solution, which I'm going to write AEIKX plus BE negative IKX, that is going to have to equal psi 2 at x equals 0. Okay, so let's set those equal to each other. So now that's C E kappa x plus d e to the negative kappa x, all right? And at x equals 0, these functions have to be equal to each other. So what happens? Well, you notice these are all e to the power x, right? And so e raised to the power 0 is just 1. So this is going to help us create one boundary condition. So in other words, wave function at region 1 has to equal the wave function at region 2. And when I plug in that value of x equals 0, look, all the e's become 1s. And so thus I get a very simple condition which says a plus b has to equal c plus d. There's my first equation that's going to be useful. Okay. All right, so then what about at the x equals L boundary, right? Well, we note that wave function 1 has to equal wave function 2 at x equals 0. And similarly, wave function 2 has to equal wave function 3 at x equals L. So now that becomes the following. So I'm going to say wave function number 2. So first, sorry, I'm going to box that off, and I'm going to call it a number 1. Okay, so now the second boundary we need to worry about here is region 2, which is going to be CE kappa x plus DE negative kappa x equals the region 3 solution, which is going to be A prime E to the IKX plus B prime E to the negative IKX. And of course, this is at x equals L. And so now when I substitute that value of L, I unfortunately don't eliminate all of these E's, but that's okay because it gives me another nice condition. That says CE to the kappa L plus DE to the negative kappa L has to equal A prime E to the IKL plus B prime E to the negative IKL. And I'm going to box off this equation, and I'm going to call this number 2. That's our second condition of normalization. Okay? So now, what about other conditions? Well, the slopes have to be continuous. Sorry, that's terrible. That says slopes have to be continuous. Okay? And specifically, the slopes have to be continuous at x equals 0 and x equals L. Okay? So now, what I want to do is, first let's do the x equals 0. And I want to take the first derivative of the region 1 wave functions. I want to take the first derivative of the region 2 wave functions. And then I want to set those equal to each other. Okay? So the first derivative of region 1, so let's do that. Okay? So taking the first derivative, and I'm only, because I know, well, excuse me, I'll just go through the full derivative. Okay? So we know that the derivative of A times E I K X is just going to be A I K, so that's going to be A I K E I K X, right? And then that term is going to be negative B I K E negative I K X. Okay, now I want to take the derivatives of this region 2. All right, so that's just going to be C times kappa E to the kappa X. And then now that's going to be minus D times kappa E to the negative kappa X. So we remember that we've defined that position to be x equals 0. And remember, e raised to the power of 0 equals 1. So now all of my e's, right, when I place in a value of 0, they're all going to go away. And now what I'm going to have is e I k minus b I k. And that's going to equal c times kappa minus d times kappa. And I'm going to call this one number 3. And I'm going to box this one off as well. There's our third and final condition. And then finally, the slopes must be continuous at x equals L. So I'm going to do the same process here, but now I'm taking the derivative of region 2 and region 3. So we already did the derivative of region 2. Let's just rewrite that. That's going to be c kappa E to the kappa x minus d kappa E to the negative kappa x. And so now we've got to set that equal to the first derivative of region 3, which is going to be a prime I k E I k x. I'm going to move this x equals L out of the way. And so now that's, minus, because there's the negative sign, right? And I take the derivative, and so the negative comes down. So now that's negative b prime I k e negative I k x. And because these derivatives have to be continuous at x equals L, I can't eliminate any of the exponentials. I just have to substitute x for L. So let's write that really quick. C kappa E kappa L minus D kappa E negative kappa L has to equal A prime I K E I K L minus B prime I K E negative I K L. I'm going to put a number 4 by that. That is our fourth condition. Let's see how we're doing here. 4 equations with 6 unknowns, right? My 6 unknowns are A, B, oops. My 6 unknowns are A, B, C, D, A prime, and B prime. 6 normalization constants I have to find, but I only get 4 equations. How the hell am I gonna do it? Well, let's think about this for a moment, okay? So in a given time sequence, what we're really only interested in solving this problem is forward moving particles. We know that we're going to have a reflected wave here, and eventually if we have some boundary right here, we're also going to have a reflected wave. But in solving this problem, right, for what I'll call forward motion, we can actually eliminate the B prime constant. We can set the B prime constant equals to 0, because I'll remind you that B prime constant, here it is in region 3, right? Because that's attached to the E negative IKX. That's a particle moving in that other direction. So we'll eliminate it. We won't worry about it, okay? Well, then what about the other left moving particles? Is that important? As it turns out, it is. These reflected waves, right, where I get a reflected wave going back the other way, or a reflected wave going back this way, those are important because they fix the probability of this particle moving in the opposite direction. So we can't ignore those. But we'll ignore, right, the particle that's reflecting all the way back here because the tunneling has already occurred, okay? So so now we've got 5 unknowns with 4 equations. How do we specify a 5th equation? Because with 5 unknowns, we're going to need 5 equations, okay? Well, we can talk about this in terms of transmission probability. What's the probability that the particle will make it through, okay? And so I'll reflect that with the letter T right here. And the probability that the particle is going to make it through, we can relate to the normalization constant in this region to the normalization constant in this region. So in other words, those normalization constants are really giving us the amplitude of these waves, okay? And so if we can see now that the particle has made it through here, and there's some finite amplitude on this side, and some finite amplitude on this side, then we know that this probability is going to, or this transmission probability is going to be related to the square modulus. I'm going to do my cool little Dirac notation. It's going to be related to the square modulus of a particle moving this way in region 1. So I'll put a little 1 right there, over the wave function square modulus of a particle moving the same direction in region 3, okay? So that now gives us a 5th equation where we're going to say the transmission probability is going to be equal to the square of this A constant over the square of the A prime constant. And thus we have a 5th equation with 5 unknowns. And then all we have to do now to normalize this, we don't have to go through and do psi squared set equal to 1, we can just normalize all of these things to each other by solving a 5 by 5 system of equations. Okay? We can do that with matrices. We can do that with Mathematica. There's a number of ways that we can solve a system of 5 equations with 5 unknowns. And that's how we normalize this tunneling problem. Okay, so that's been going on for a while. I do have just a little bit more to carry on related to this transmission probability. So I'll pick that up in a second part of this lecture. Okay, folks.